This is Unit 8.1. It deals with vehicles and cars in particular. So the key idea here is forces predict motion. So there's all kinds of forces on cars, and if we understand the forces, we can understand the motion. So cars, by cars we obviously mean vehicles of any kind, trucks and so on. And the first thing is to think about acceleration and speed and the implications those have for safety. So decelerating is also important. If we want to be safe, if there's a problem, we need to be able to stop, and we need to be able to stop safely. So we have crumple zones and we have seat belts to help us do that. And then here we have our understanding or analysis of stopping. So stopping distance is the total distance from the moment you see a problem like a falling tree to the moment you actually stop. And it's made of two things: thinking distance, so the time while you're or the distance you're traveling while you're thinking. So it's a very short time, but you still travel a significant distance. And then braking distance, which is from the moment you hit the brake to the moment you actually stop. So this is while you're thinking, this is while you're braking, and together they make stopping. Now obviously the better your reactions, the quicker you'll start braking, or the shorter your thinking time will be. Now braking is related to speed squared, because it's fundamentally about energy. You're getting rid of kinetic energy, and you need a force to do that, and your braking force is constant. But if you double your speed, you actually quadruple your energy. So it's slightly against common sense, and that's why the driving test really tries to emphasize that to you. So firstly, the board wants you to have some sense of typical speeds. So we've got a little table here to try and give us a sense of that. So walking speed might be 1 meter per second, cycling a bit faster. An Olympic sprinter will do 100 meters in 10 seconds approximately. Now obviously they speed up and slow down or whatever, but an average would be 10 meters per second. Hurricanes, a full-on hurricane can be 70 meters per second. A supercar, very few of those, but they might go 100 meters per second, and sound travels 300 meters per second, although there are some very exotic specialist cars, rocket cars, that can go at that speed. And finally over here we've got what I think is an interesting graph that shows us marathon times, and they show that they come down, and generally the peak of an athlete is here in their late 20s, although in the 30s and 40s they do pretty well, but then it steadily increases there on the aging side of the graph. Now acceleration, also electric cars are becoming increasingly popular, but there is a racing series, and that actually holds the record at the moment, 0 to 60 miles per hour. So this is dealing with imperial units. In Britain we do that. So this is another way of specifying acceleration. The more physicsy way of doing it is to talk about meters per second per second. Now in contrast, a Toyota Corolla Verso, a pretty average family car, will do it 3 meters per second per second. It would take you a little over 9 seconds to reach the same speed. So, and we have a variety of cars in between. So coming back to this point, in Britain we do have miles. They used to be part of an incredibly convoluted system here called the imperial system, although feet and inches still survive, and fathoms in certain circumstances we talk about. But in general, the system international is more logical. So we have meters and kilometers, decimeters, centimeters, millimeters and micrometers, which all relate to each other in a very exact way. Now the French even tried to decimalize time. They tried to have 10 hours or 2 lots of 10 hours in a day, but the French people drew a line under that and said, no, we're not going to decimalize time as well. So reaction times, 2 sort of classic experiments: dropping the ruler here. A second person drops the ruler, and you see how quickly you can react. So typical reaction time is 0.2 seconds, or we can have an electronic version of that. Now that is relevant to our definition of cars. So we mentioned this in the intro, but we've got 2 scenarios here. We've got the perfect scenario and the nightmare scenario. So in the ideal scenario, you're traveling slowly, you've got very good, well-maintained car, it's not overloaded, and you're sober and alert, and you stop quickly. The nightmare scenario is you have an old car, it's not very well maintained, it's overloaded, you're drunk, you're tired, and you're going too fast, and your distance is going to be much further. So we can see that on this graph. So higher starting point, longer line here shows longer to react, and the area under the graph is the distance. And then when we do start braking, we see that the gradient is less, and it's a shallower gradient, so it takes longer. So alcohol might be involved, poor brakes, an icy surface would all make it worse. So this summary table here shows the factors. So we've got three key factors: the driver, the state of the driver, the state of the car, and the state of the road. So the driver, we want the driver to be, as we said, well rested. The car, there's three aspects of the car. So the speed, the mass of the car, how loaded it is, and then the quality of the brakes and the tyres, and finally the state of the road. So in terms of affecting thinking distance, the state of the driver affects thinking distance, as does speed, but nothing else. Is the mass, the quality, and the road don't affect thinking distance. Braking distance, the driver, as far as the board is concerned, a drunk driver can hit the brakes just as hard as a sober one, so don't make that a factor in thinking. As you can see, speed is highlighted in green. It affects both, which is why it's so important to highlight speed as a danger factor. But then the mass, the quality of the brakes, and the state of the road all affect braking distance. By the way, make sure you don't say state of the road in the exam. Describe the state of the road. So an icy road will increase braking distance. Card. So here we've got this very rapid or disproportionate increase in the braking distance, the red, and we mentioned this in the intro. It's to do with energy, half mv squared. So if you double the speed, you quadruple the kinetic energy, so therefore you have to quadruple the distance, because the braking force can't change. Yeah, so fundamentally braking is about dissipating energy, turning kinetic energy into heat energy, and as we said, this quadrupling is a key thing they want you to think about. Doubling speed quadruples energy and therefore quadruples braking distance. So we've got decelerations here. Decelerations, extreme decelerations, are very dangerous. They result in large forces, which result in injury. So we want decelerations to be gentle. So we can see that here, this old-fashioned car protected itself, but probably not its occupant. A modern car is designed to be deliberately weak, and that's the crumple zone, and it acts like a pillow essentially. We can see that here. So this red car hits the wall and deforms a bit, but comes to a halt in a very small time, which means a very large force, whereas this one has a much larger time, a longer time, and therefore a smaller force. If you think of a cricketer catching a cricket ball, they do something similar. They cushion it. So here on the graph we can see the spike is much more extreme. The maximum force is much more extreme for the red car. Now a similar thing applies with seat belts. Now on the top one there is no seat belt here, so the deceleration is over a very small distance. It's the dashboard and the glass that does the decelerating, and we can see the calculations here. 150 G's, so 150 times the acceleration due to gravity, or 10 tons, a huge force to experience. Now a stretchy seatbelt, still uncomfortable no doubt, but it's over a much longer distance and a significantly longer time, and therefore it spreads out this force and is therefore much safer.